So today we want to talk about electromagnetic radiation. So this is the idea. We have an oscillating charge, and that's going to create an oscillating electric field, right, as it's moving up and down. It's also going to create an oscillating magnetic field. Because if we think about this charge going up and down in this metal pole, you can kind of think of it as a current going up and down. So if I have my metal pole here, I think that black's going down. Let's see if the blue works better. Get my eraser. All right, so if I have my wire here and I have my current, it's going to be oscillating. So first it's going up and then it's going down. But when it's going up, what kind of magnetic field is it going to make? Right? Which way? Your thumb goes in the direction of the current, your fingers show the direction of the magnetic field. So the magnetic field, when the current is going up, is going to be this way. So it's going to be coming out of the board on this side and into the board on that side, right? So I get magnetic field lines that go out like this. And then what happens? Then the current slows down and turns direction, and now which way is the magnetic field? It's opposite. So when it's going the other way, the magnetic field over here is into the board, and it's over the board over here. Right? So I'm going to get a magnetic field first going this way and then going that way, and of course it's going to be changing in value, so I have a changing magnetic field. Right? That, according to Faraday's law, gives me what? Remember the rate of change of the magnetic flux over time with a minus sign? What was that equal to? This is Faraday's law of induction. It's equal to a voltage. You remember this? Epsilon? But a voltage we can really write as an electric field, right? An electric field around the loop. And so this changing magnetic field here is going to create a changing electric field perpendicular. Right? That's what's happening. That's what's creating, and we saw that in the video, right? That oscillating electromagnetic field from the changing of the current going up and down. That's going to create this oscillation. So this one is showing me the electric field. And it's going up and down, up and down. We could turn on the static field instead. What's the static field? That's just the field that points right to the charge, right? This isn't the negative charge, so it's pointing in. So this is the static field, but it's also going to cause ripples in the electric field, and that's the radiative field. Right, so I'm transmitting that radiation out. So I'll turn back on the radiative field. And you can see that's what the oscillating radiative field looks like. Right, it's being sent up. You can see it oscillating. It goes up and then it goes down. Right, it's going at the frequency here. But you can see it's got a change in value right here. You can see that the trough is moving this way. Now the crust is coming through, and we can pick it up over here, right, on this charged particle, because you can feel the electric field. Right. This is what happens. Anybody remember seeing pictures of the original cell phones? They're those big bricks, and they had an antenna going up. Anyway, that's what it was, right? As you're talking, you're creating an electric field going up and down, or a current going up and down in that antenna. That's sending out to the cell tower. The cell tower is picking it up, right? And then it sends it back, comes back into your antenna. Nowadays, antennas are more sophisticated. They're not just straight poles. You can have dipole antennas, different shapes antennas. So this is just showing me a simple example of a pole antenna. But the idea is the same. Okay, we can see the curve with vectors. So there it's showing you kind of what it looks like. Okay. All right, I have some other examples of this. Here's just another visualization of what's going on. This is showing you both fields, the electric field and the magnetic field, because they go together. And you can see this is going up and down. It's creating an electric field going up and down. That creates a magnetic field transverse And notice which way is the wave going? Perpendicular to those two fields, right? So it's going to produce this oscillating wave. No. Where's the one I want? Oh, this is the one I want. It's going to produce these oscillating waves, the electric field and the magnetic field, perpendicular to each other, and they're also traveling perpendicular to that. We're going to go back to physics 1 for a minute here. What kind of wave is that? We have two types of waves. Anybody remember? It's a transverse wave, right? It's on a longitudinal. Sound is a longitudinal wave. The electromagnetic wave is a transverse wave. So it's going up and down and up and down. An equation that you probably remember from physics 1, or I hope you remember from physics 1.
Friction?
No, but it does have an F in it. The speed of a wave is equal to, anybody remember?
Force?
Nope. F times lambda. What's F? Frequency. And lambda is wavelength. And the speed of wave is frequency times, that's true for all waves, including light waves. For light, my velocity is not just generic v, it's c, which is frequency times wavelength. And c, anybody remember what c is? I gave you the formula on Friday. Matthew left. He got in trouble with his mom.
I was in trouble.
I'm telling the class.
She was just mad because it doesn't matter. We'll get back to it.
We'll get back to it. Come on, I have to throw a little shade, but that's fun. Epsilon naught, mu naught. Anybody remember that? So it depends on these two constants, which gives me approximately 3 times 10 to the 8. That's an exact value, but it's close. 3 times 10 to the 8 meters per second. So that's the speed of light. It's a wave, and we have this transverse wave, and you can see it's propagating perpendicular to each other. Okay? So far makes sense? Yes, ma'am.
Do they always have the same magnitude?
They make it look like the magnitude is the same here, but it's not, because they're in different units. One's in volts per meter and the other's in Teslas.
So it's not like...
But they are related.
Wave. Yeah.
They are related. E over B is equal to C. Hey, dear. So this is the relationship between the electric field and the magnetic field. They're connected by the speed of light. Because that's got those constants, epsilon naught, mu naught. Does that make sense? U would be a C. Okay. Let's see some more examples of this oscillation. Some examples of another antenna. Here's a dipole antenna. I'm zoomed in, but you can see it's very similar, but instead of having one long pole, I have 2 shorter poles, but I make one positive because it's on the positive side, one negative on the negative side. I'm kind of extending one pole into 2 poles here. Does that kind of make sense? That's a dipole antenna. Okay? You can also have, I think, circular antennas, like loop antennas. There's lots of different shapes of antennas. There's a whole field. If you go into electrical engineering, it's designing antennas. You design them to pick up the frequencies you're interested in. Right, so I don't know if you've ever seen, antennas used to always be long, straight things, like on cars. The old cars from the 80s had the long, now they got the cool little fins on the back, right? You know what I'm talking about? The little fin on the top of your car, that's your antenna now. Probably, I think it's a loop antenna. I'm not sure of that. I don't design antennas. But there's lots of different designs, right? And you transmit a wave, and then you can zoom way in so you can see, this is going on. Right, but it's creating this oscillating electric and magnetic field. This is just showing the electric field. Okay? Now we have lots of different frequencies we can go at. We can go at faster or slower. If I go back to my other one, I think I can change the frequency on that one. So let's change the frequency. Let's make it very fast. So I have a very high frequency, relatively speaking, or I can make a very low frequency. Well, that's 0 frequency. There's a very slow frequency. Whoa, it's trying. Right? I have very high and low frequencies. That means for the wavelength what? I can have very high and low wavelengths, right? But even though it's oscillating very slowly, the wave propagates at the same speed. Right? It's the speed of light. Does that make sense to everybody? So the speed is the same. Other way. This gives us the electromagnetic spectrum, which you can see here. Or maybe we can make that a little bigger. Control plus. Yeah, there we go. Okay. So you see, we start down here. I'll start backwards. This is very long wavelengths, 10 to the 8 meters. That's huge, right? And then kilometers, 10 to the what? 3. And mega is 10 to the 6. We're talking about bigger than a megameter. I mean, this is huge, right? Long wavelengths. Very long radio waves over here. Your ham radio is probably in here. Everybody know what ham radio is? When they would listen to like the CB truckers and the radio thing, you can bounce off the atmosphere and talk to like Europe. Anybody know what I'm talking about?
No, but that's cool.
You seen the World War II movies? When they're tuning in the radio? Those are ham radios, and they have really long wavelengths, and it bounces off the atmosphere, so you can talk to Europe through these radio waves, right? And then you get into the AM and FM, and radio waves, TVs, I think over here, if I remember right. So these are 10 to the 2 meters, which is right just under a kilometer. Thank you. Brain freeze. Question, Mary? Right? And then 10 meters for radio waves. Then you get into the microwave region. So 10 to the minus 2, which is a centimeter, right?
Is it the actual ones that we have in our microwave?
Yeah, that's what you cook with.
Oh, really?
Yeah, you cook with microwaves, and this electromagnetic radiation is about 10 centimeters big, roughly, in that range, right? Try this experiment at home. Take a chocolate bar, heat it in the microwave, and if you don't want it spinning, you want to put it on a flat plate, right? Because it'll set up a standing wave in there, and you can see where the
waves are.
The waves are. You can see the node points. Well, actually, the anti-node points. We're getting the most magnetic, because that's where the most energy is deposited, and it'll melt there in those spots. So you can test that with a chocolate bar. You can measure the speed of light with a chocolate bar. If you knew the frequency of the microwave and measure the wavelength, that's half a wave between those points, and then you can get the speed of light. So it's something to try. Right, and then you get into microwave. So this is also telecommunications. Your cell phones and stuff are in that microwave region. That's what there, I always look at my phone. That's what my phone's sending out, microwave, when it's connecting to, Wi-Fi and cellular and stuff. It's in that region. Well, cellular is, I don't know where Wi-Fi is. I think Wi-Fi might be longer. But anyways, cellular's in there. And then we get to infrared. Right, almost visible, not quite. This they have in the calf. Anybody know where they have this in the calf?
For the food?
Yeah,
The food?
Those heat lamps over the food, they give off visible, some visible, you can see the food, but also infrared. Body temperature absorb, at infrared, that's when we give off radiation. That's kind of when things absorb a radiation. So that is really good for heating food, by keeping it warm. Then we get into the visible spectrum, and you can see this scale is not linear, right? Because this is 10 to the 8, 10 to the 6. This is the log scale, power 10 scale. So we have a very narrow band that is the visible spectrum, from just under 400 nanometers to about 750 nanometers. So we're talking like 300 nanometers range is everything we see is in that band. All right? Everything around us, all the light we see is oscillating electromagnetic fields in this frequency range. This is what our eyes pick up. Right? And then we get into ultraviolet. Right? This is what gives us, you gotta put that sunscreen on. Right?
No, I'm good.
It also helps make vitamin D though. Right? Did you guys know that from biology?
Vitamin D.
And there's animals that can see this. Anybody know what I'm talking about? The bees.
Bees, yeah. Oh, the bees?
Bees see ultraviolet. They see more light than we see. So when they look at flowers and stuff, they don't just see the visible light coming off the flowers, they see the ultraviolet, so they see differently than us. Because their eyes are different. So bees can see some of the ultraviolet, not the whole thing, but some of it. Right? Because ultraviolet starts right here after the violet. So, and then we get X-rays. That's where you go to the dentist, right? You take a picture of your, and then you turn into a hawk. Notice this is small. 10 to the minus 10. That's about the size of a nucleus, or sorry, size of an atom. So it's the atomic scale. And then down here, 10 to the minus 12, 14. I think somewhere in here is the nuclear scale. It doesn't make you the Hulk, really.
I don't know why my brain never processed that since there's X-rays, there's gotta be Y-rays. Or is that what that counts as?
No, that's gamma
That's
rays.
gamma.
Yeah.
That's okay, I was about to say.
Yes, Dio first, and then Mary.
Yeah. Quick question. So, if you go to Y rays, the gamma rays, does it mean that it's going to get hotter? Like, is it related to temperature at all, or no?
It can be, yes.
Yeah.
Because remember we talked in physics 1 about the
Temperature.
power radiated of an object?
Yeah.
You know, the E sigma emissivity, Boltzmann constant, temperature to the fourth. So, and then we'll see, yeah. So the higher the temperature, the shorter the wavelength of light it peaks, it gives off. We'll see that on another graph. Query, question.
When there's like a nuclear leak in a power plant, what would it like?
Most of that is, I mean, there's probably some gamma, but probably a lot of it is beta and alpha as well.
What does that mean?
Which is before.
It's different type. So beta is a helium nucleus coming out.
Okay.
So you have a big rate like uranium, and it pops out basically a helium atom.
So it's not necessarily the EM spectrum?
No, just the gamma is. So beta is electrons coming out, and alpha is helium nuclei coming out. But the gamma is. This here, the reason it's bad is it breaks apart your DNA.
That's what happened in Hulk.
That's what happens in the Hulk. But you don't turn into a Hulk. You get radiation poisoning. Your DNA can't replicate, and so eventually all your cells die out because they can't reproduce. They can't function. They can't open properly and do the protein reading. So your cells stop functioning properly, and you.
It can't break
Radiation
glucose
poisoning.
anymore, right?
What?
It can't break glucose anymore.
Yeah, I mean, right. It disrupts the whole system. Because you break the DNA, you can't do anything.
Is it only in a lab, or are there like places that you can go where there's gamma radiation?
I mean, yeah. So like, I should have brought. I have some gamma radioactive sources,
Oh Jesus.
but it's low dose. So we don't have to worry about it.
We're okay. Thank you.
Yeah. So I mean, we're getting radiation from the ground. Just there's elements in the ground. We're getting alpha, beta, gamma, but not high doses where it's going to break enough DNA to cause problems.
Think that.
Did you know that today is your day, apparently? It's World Quantum Day.
Is it World Quantum Day? Oh, I gotta look that
And
up.
I immediately thought Dr. Browning's Day.
I love quantum mechanics. Let's see. What was I gonna say about gamma radiation? I'm gonna say something about it.
You're gonna have us watch that one scene from the book. It's supposed to be.
No, but there's an old movie about the making of the atomic bomb. It's like Fat Man and Little Tater or something like that. Because that's what the two bomb names or something like that. You know, the two bombs they developed for Hiroshima and Nagasaki. And one of the guys working on it, he got overexposed and got radiation sickness. So he showed you what happens. It's not a pleasant way to go.
What did the guy intentionally make it for again? Not the bomb, but the guy that led up. It led up to the bomb. I know, like, the original purpose wasn't for, like,
Oppenheimer?
stuff like
Well, Oppenheimer developed the bomb.
Yeah.
Enrico Fermi, he made the first controlled reaction in Chicago under the football stadium. Soldier Field. You ever been to Chicago? No? Okay, Chicago. You've been to Chicago, right?
Well, just the airport. It's not.
All right, go to Chicago. Downtown on Lake Michigan is Soldier Field. It's the football field for the Bears. Underneath, they developed the first nuclear, in top secret, radioactive
Why
sustained.
underneath the football field?
Huh?
Why underneath the football field?
I guess it was, nobody suspected to look under there. It was a hidden location.
Was it the first what?
It was the first, like, sustained nuclear reaction. Enrico Fermi. That was the start of
And then
the.
that led to.
Yeah, it was the start of, okay, we got to get this going, then we got to speed it up, and that gave us the bomb, but that was the first kind of step in making the bomb. So, all right. Here's another picture of the spectrum, and this is showing you the heat of the object. The hotter the object, the peak radiation is going to give at different spectrums. And so you can see here again is the wavelength. Here's this is just a picture. This is the wavelength. This is the corresponding size of object, so you get a sense of what it is. So microwave, like, butterfly size, 10 centimeters, right? Radio waves, we're talking buildings, right? So buildings don't interfere with radio waves, or if you drive through the mountains. Anybody ever listen to the radio anymore? FM, AM? The FM radio gets chopped out by mountains or buildings because they're on that size. If you have a wavelength the size of the object, you can kind of see that object with that wavelength. Right? So radio waves interfere with buildings, but a butterfly is not going to interfere with a radio wave. Right? And so we get down here to the kind of the spectrum is on the size of cells. This was really convenient because Leeuwenhoek, you remember Leeuwenhoek from biology?
Maybe.
He invented the microscope.
Yes.
Right? And he was able to see the microbes in the water using a light microscope. But you can't see smaller than that. Luckily cells are that small, we can see them with light. But if you want to get inside and see all the small intricate parts of the cell, inside all the mitochondria, you can kind of see the mitochondria with a microscope, but if you get much smaller, you can't see like pores and things. You would need a higher wavelength, right? To see atoms, you can't see atoms with light. You need X-rays to see atoms, right? Molecules, you need ultraviolet. And then to see nuclei, you need gamma radiation. Okay, does that kind of make sense? You can see how small something is with a wavelength of that length. Right.
So when we take like a CT or maybe we go to the dentist and take an X-ray, can they see like our atoms?
Well,
Using an X-ray?
they're collecting a bunch of data because they want to penetrate the skin because the skin bounces off the visible. So the bones, they interact with the X-ray more.
Oh, interesting.
Than our skin does.
So they reflect, right? The bones would reflect X-rays?
I think so, if I remember right, I think.
That's really interesting.
So, yeah, but this is in chemistry when you do ultraviolet, UV spectrum, okay, molecules. If you want to find atom location, you do X-ray spectroscopy. I think it's the word. Okay, so that's the electromagnetic spectrum, and the frequency down there. So that's the idea. Let's see. Okay, let's go back to our wave. This one. Okay, so the wave is oscillating. And, after we go to our first simulator, let's speed this up a bit. So we get some real, that's a little crazy. Let's go, that's nice. That looks good. So here it comes. And we're seeing the radiative field and the curve. So what's going on? I'm making this current go up and down, right? That's creating electric and magnetic fields. What we learned earlier this semester, electric and magnetic fields can contain energy. Right? When I built a capacitor, I stored energy in the electric field. That energy now is in that electric field, but that electric field doesn't stay here. What's it do? It's traveling. So I can take energy from one place and send it to another place through this oscillating electromagnetic field. So this wave is carrying energy. Right? Does that make sense to everybody? And notice that energy is being picked up over here, creating current. Right? So I can transmit energy this way. Right? That rate of energy transfer comes into what we call the pointing vector. Not pointing like direction, even though it is pointing in a direction. It's P-O-Y, how do you spell it? P-O-Y-N-T. P-O-Y-N-T-I-N-T. So it sounds like pointing, but it's the guy's name. Right? And the pointing vector S is equal to, I don't have it memorized, I gotta write it down. It's 1 over mu naught E cross B.
This S is totally different than entropy, right?
Yes, this is S vector.
Okay.
Yeah, it's the pointing vector. And it's showing me the direction of the energy flow. Right? Because it's E cross B. Well, if we go back to our other picture, what is E cross B? Right? If I pause this for a minute, there we go. Okay. Right, let's say this is E, the green This is the magnetic field B. How do we do a cross product? You may remember? Curl the first into the second. Curl the first into the second. Which way is? That's the direction of propagation. E cross B. So S is pointing in the direction of propagation. Okay. And the units for S are joules per second per meter squared, or watts per meter squared. Okay? So it basically is power per unit area. Is what this pointing vector is telling me. It's telling me how much power I'm transmitting per unit area of space. Okay. If we average S over a cycle, so if we just look at S from one crest to another crest, we get the average S in there, we call that the intensity, I. So it's kind of the average energy, rate of energy being deposited per unit area over a cycle. Does that kind of make sense?
Can you
That's
say
the
it again?
intensity, huh?
What's the intensity?
It's S averaged over a cycle. Right, so if I take a whole cycle of the wave, right? So if I maybe I put something here and I absorb a whole cycle of wave of light coming in, then I would get the intensity of that light. All right. So it's kind of the energy being deposited per unit area. Okay. And you can see that the I, because we're going to average over a whole cycle, ends up being E max, B max. The max electric field, E max electric field over 2, I think it's mu sum naught. Yeah, mu sum naught. Right, so because we're averaging, looking at this, of course it's going up and down, so we gotta do square root of 2 on the E, square root of 2 on the B, that gives me a 2 instead of the square root of 2. Because we gotta use root mean square. So that's where that 2 comes from. And then we're looking at the energy stored in the electric field and the magnetic field.
That's E and B what? Max.
E, yeah, so it's the max of those vectors. Divided by 2 times mu naught. And then using this formula, this formula here, you can write it all in terms of E or all in terms of B by replacing E with, right? I could say, okay, E is equal to C times B. So I could write, instead of E max, I could write this as B max squared times C over 2 mu naught. I just replaced E with B times C. Or you could replace B, whichever one. Same idea. Okay. Your book does a long derivation on power. I'm just going to give it to you. Or on the momentum, because this thing is carrying energy. When it hits something, what's it going to do? It's going to deposit the energy. Well, the depositing of energy is like applying a force. So there's momentum carried with this wave as well. And the momentum of the wave in magnitude, and if I remember right, it is the pointing vector, over C. And this is per unit cycle. So actually you could write it as I over C. Because I'm going to do it over a cycle. If you want the instantaneous momentum, that would be S over C.
C in this case is going to be the speed of light?
Yeah, C is the speed of light. So, this electromagnetic radiation, it can carry energy and it can carry momentum. But you can see the momentum is usually pretty small because we're dividing by C. C is a big number. So usually you don't feel the momentum of light hitting you, right? Here on Earth. But they use this in outer space when they had those solar. They can extend out those long solar cells. but that can pick up the solar wind. Basically, the light hitting it, there's no resistance in outer space because friction's big here on Earth, right? In outer space, there's no friction, so it can absorb the light and then use that transfer of momentum to move the object in outer space. So you have these giant solar cells that you can put on things to help things move. Your book discusses that somewhere, I thought. Maybe not. Oh, space sailing. Yeah, they talk a little. They have a couple paragraphs on it. Okay, I think we'll skip polarization. Maybe you have a homework on it, but that's not super exciting. The pointing vector is pretty cool because it tells me how the light is traveling. So that's a pretty handy quantity. And it's a cross product. All right. So that's pretty much the end of chapter 24. Question, Mary?
So since the pointing vector is power per unit area,
Yeah.
if you could find the area.
Yeah, so, right, so you have light hitting a surface. You know the size of that surface, you can figure out how much power it's absorbing.
Okay, so that would be how you would sort of calculate power.
Yeah, right. Yeah, being the power absorbed. You take the intensity or basically the pointing vector, magnitude times the area. Yes. Question?
Yep, I think we have 2 homeworks due this Sunday.
Okay,
Right.
let's fix those.
See if you can fix those.
Yeah.
And also, we're not gonna have lab on Friday, right? No
You
lab.
know what, just take off Friday, my turn.
Thank you. What about Monday? Can we take off Monday?
Okay, just for Dio.
Thank you.
So Friday, Monday off,
No class on Monday.
and then we have 2 weeks left, is that right? After
That's
this?
insane.
For 2 weeks and then finals, so 3 weeks.
Okay.
Yeah, but 2 weeks of lecture, and we're missing Monday.
Yeah.
So the opposite's gonna go real fast. I mean, we're gonna have to hit the ball running on that.
Yeah.
But we're gonna do reflection and refraction. That's chapter 25, but that's actually pretty fast. 25 is a tiny chapter, so we can hit that easy. And then we'll move into chapter 26. I don't think we're gonna get I want to get 27, but I don't know if we're gonna get 27.
What's 27?
Wave optics, so we're looking at interference patterns, diffraction patterns. I might do as much as I can in 27.
And for next exam, we're gonna have from induction. To
Induction to as far as I get.
optics. Okay. Does it include RLC circuits?
We didn't really talk about RLC circuits, right?
Okay, yeah, not that much.
No, I talked about it more in the other class. Your book doesn't cover it, which is a shame. But your book does the whole pointing vector stuff and cross product. They don't have the pointing vector. But you're going to get RLC circuits in the electronics course.
Yeah.
So I'm not too worried. You'll see that stuff. All right, let me log in the 7 gauge and move this around. And then we'll get going early here in a minute. Because I don't want to start like, I think I can do all 25 on Wednesday, really. So take the whole hour, because it's super short. It's just, reflection's like, it bounces off, done. Refraction's got a formula, but it's one formula, and then you just apply it in different scenarios, so. 25 is probably your shortest chapter of the whole book. Alright, so we need to move homework around, you said, right?
Yep.
So let's do it. And then we need extensions again. Everybody good on, you need extensions?
Yeah, the last homework that was due, yes,
Okay.
but I finished it.
You finished the other ones? Good.
Yeah.
Alright, so let's do, this is, only one's due Sunday, it looks like, right? Am I in the right course?
Yeah. That one was due yesterday.
Oh, that was due yesterday. Oh, I gotta look at the coming one.
Yeah,
Oh.
you see?
Oh, this one's gotta move. Cause you can do,
But that will be
you can do electromagnetic wave.
Okay.
That's what we did today.
And then we do wave optics after the break, right? Which is going.
Yeah. I might move reflection and refraction back because we might finish that Wednesday. It's real short.
Really?
I mean, it's like 8 pages. It's a super short chapter. 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's more than 8 pages.
Yeah.
It's like 15 pages, but it's super short. And there's only one equation.
Can you reopen magnetic fields for me?
I can reopen magnetic fields. just because I'm a nice guy and you got yelled at by your mom, so I feel bad for you. I'm just teasing. Okay, so which one?
Magnetic fields. It was 22.
I'm trying to figure out how to do it without showing everybody their grades. I don't want to show everybody your grades, so I gotta go to squad view to do this. So which one? Matthew?
22. Magnetic fields.
22.
So we have 3 more homeworks. And can you open up 23 for me?
Let me deal with Matthew. If you guys can go, the rest of you, you don't need me to send the homework. Don't tell anybody that you leave early.